Hi! Induction cookers are great at heating ferromagnetic metals fast, but I'm more interested in their magnetic field. This dirt cheap induction cooker is basically a 2000 watts AC electromagnet. I wonder if it can be used for magnetic levitation. Let's find out. Playing with induction cookers in ways not intended can start fires near high voltage. And also be aware of stray high wattage electromagnetic fields. If you are familiar with induction cookers, you probably know they will only work if something large and magnetic is placed over them. You can test if cookware is suitable for induction cooking by simply placing a magnet on the base. If the magnet sticks firmly, the cookware base is ferromagnetic and therefore suitable. And relatively heavy since it contains dense iron. The weight is actually an advantage since induction always creates an opposing magnetic field that can make highly conductive metals hover, magnetically levitate when using AC. It is hard to levitate heavy iron. Light aluminum is easier, but induction cooktops detect if proper cookware is placed on them, for several reasons. Let me show how this cooker reacts to aluminum foil, also known as tin foil or sølvpapir. Starting with 11 microns thin foil, it shouldn't turn on, right? Well, the detection circuit is not perfect, giving us the first sign of levitation. After flattening the same piece of foil, I filmed from the side, giving an even more interesting result. This is promising, but the flattening of the foil might not be a good idea. Watch carefully. That is scary. Don't try this at home, please. The aluminum quickly got red hot before it levitated away. Let me switch to a little more rigid 15 microns foil. First, non-flattened. Yeah, still seeing a potential for levitation here. Now, flattened 15 microns foil. Wow, beautiful glowing hexagram shape forming. Why is this pattern formed? Aha! The pattern shows how effective the field concentrating ferrite bars under the induction coil are. But heating is not what I'm aiming for. I tried several other aluminum pieces to see if they would levitate, but the cooker refused to turn on. Only a large alufoil tray worked really well, actually.
It's getting hot.
For some reason, only very thin aluminum fools the cooker into turning on. I will attempt to explain why later. Before that, the high sides on the well-working tray inspired me to try not a tinfoil hat, but a tinfoil crown. This shouldn't work. There's very little metal near the induction coil. Okay, the cooker does turn on, but not a big jump. Probably too much inactive weight in the crown, too far away from the coil underneath. How about a lower crown? Oh yes, highest jump yet. Maybe it can be improved with a guide, like an alucan. Maybe a little more weight is needed. Nice! Looks like the alu ring is hovering as the alu cans sneak away from the coil area. How do soda cans react alone? I tried several combinations, but the cooker wouldn't accept them as cookware. Until this combination. What is going on here? Long-term viewers might remember something. I'll reveal why this can acts up later. First, I would like to try a non-metal glass guide. Yes, I am happy with this on an unmodified cooker. No, it is not stable untethered levitation. That would require a faster tunable feedback loop in the cooker. But this definitely is an example of electromagnetic levitation using only things found in a kitchen. Jumping for joy! Let me know in the comments if you have any ideas for improvement or further testing of this setup. I will try some of them in a future video, so consider subscribing for that. For now, I would like to attempt to explain why thin aluminum foil fools the cooker, while thicker aluminum doesn't. I haven't found a solid confirmation, but I think it has something to do with electrical resistance. In particular, the skin effect for high-frequency AC electricity. Ferromagnetic metals have a dramatic skin effect where high-frequency current only flows near the surface, not in the middle of the metal. This effect increases the electrical resistance since only a small portion of the conductor is actually used. Resistance is similar to friction and causes heat. Useful effect for a cooker. Aluminum is not ferromagnetic, giving it less skin effect. But if very thin aluminum is used, thinner than its skin depth, even aluminum can have high resistance at high frequencies. I have calculated the so-called surface resistivity for some common induction-friendly cookware metals. Grey cast iron and ferritic stainless steel at 24,000 Hz AC, often used in induction cookers. These metal alloys range from roughly 2 to 8 milliohms per square. Now the big question is, where is aluminum on this chart? Well, 5 mm thick aluminum is here, 0.05 milliohms. Very little resistance and not fooling the cooker. How about 11 microns thin household aluminum foil that does fool the cooker? It is here. Aha! At 2.5 milliohms, it is in the range of ferromagnetic cast iron. I think the cooker is having a hard time telling aluminum foil from cast iron cookware. The cooker's detection circuit is not measuring the cookware directly for ferromagnetism. It measures indirectly by monitoring the inductance in its own coil. In my opinion and experience, a little too indirect a way if meant as a safety feature. After a short message, I will explain why this soda can is acting so differently. A huge thank you to all my patrons. I appreciate your help with keeping these videos like this one coming. For just $1 a month, you can help me out too and get full access to all my posts on patreon.com. Link in the description. Thank you. Alright, one can quickly rolls off when the coil turns on. The other slowly seeks the center, keeps the cooker turned on and gets smoking hot. What makes them act this differently? Well, the one repelled away is an aluminum can. The other is a much heavier ferromagnetic steel can. You may remember it from a video on how aluminum reacts to a permanent magnet. If not, I recommend you watch that one next. Or perhaps the video where I place an SD card on the induction cooker. Will the data survive this? Links in all the usual places. Hope you enjoyed this video enough to click like and perhaps subscribe for more like it. In any case, thanks for watching. Bye for now.